my name is Kate, and I'm a postdoc at ASTRO UWA. I'm also a principal investigator for the MAGPI Survey, leading this collaboration between our theory, cosmological simulations, and our exquisite observations, which we've just heard a huge amount from Trevor and Chenwei, so thank you for doing the hard introduction for me. As you can see, I'm just going to take this point home again. If you can leave with anything, it is this. This is a really big, multidisciplinary team, and we're a really open collaboration. So to echo what Amelia and Luca were saying yesterday with regards to geckos and mauve, we would love it if anything sparks an idea from you. Please get in touch, talk to any one of us. We're really excited to talk about our science and share that with you. But today my aim is to talk a little bit about the bridges we've been building between theory and observation in this survey. I'm going to try and convince you that such comparisons are beneficial to us all. I'm going to show off some of the data we've been preparing and give you some examples about how we've been using it. Okay, so why should you care? I'm going to proffer that simulations are an excellent tool for testing and evaluating theories about galaxy evolution. However, I have a secret to share with you all. Simulations are not a solution to the whole universe. We've got some wonderful limitations due to the range of scales in the universe that we're trying to simulate. And just as observations have a range of caveats and limitations, so do our simulations. But I have good news. This is a good thing. Not only does it keep us in a job, it also enables us to build experiments and test our theories as scientists. Of course, it's important to make sure that we are using the correct simulation to evaluate our correct theories, and vice versa, so it's always important to start with lots of voices and a science question in mind. But with these limitations in mind, we can use simulations in a really effective manner to help inform and evaluate our observations. So for example, this work back from 2020, we used mock observations of high-resolution N-body models, in particular, for which we confidently knew the underlying kinematic structure to design a correction for the effects of seeing on observed kinematics. So we all know that the blurring effects of the atmosphere that change night to night when we're observing observations for a survey here, the SAMI survey, can cause our measured kinematics that we've got on the y-axis to be suppressed, but by different amounts depending on the underlying light distribution and projection angle of the galaxy we're trying to observe. So we can see here in the spin ellipticity plane how objects move in this space due to different amounts of seeing due to the color on of each point in the plot, from their hollow points up to their corrected points when we've used this correction. And I will just remind you, down here we've got our slow rotators, those round and dispersion supported systems, and up here are those flat and rotation supported systems. Okay, but this doesn't just go one way. In that scenario, we use simulations to help inform observations, but we can turn this around. Our observations can also help to inform developments made in our simulations. And how do we start to evaluate this? So from the MAGPI survey in particular, as Trevor mentioned, we would like to explore the effects of environment at a critical epoch in time, and for this we're going to require cosmological simulations. So all of these simulations up here broadly reproduce the general properties of galaxies at redshift 0, but they will use very different ingredients to get to that end result. And as a result, they will paint slightly different pictures at that critical epoch that we're looking at, 3 to 4 gigayears look-back time, where MAGPI is going to be giving us some absolutely, and already is, some exquisite data. Now, I will say it is important to remember that one of these simulations is not right and one is wrong. Just as galaxy evolution is a complex system of cause and effect, there are many threads to untangle in this question. To demonstrate this tangle of web, I'm going to use my simulator's cookbook, which was inspired by Jess Thorne's figures for depicting variety and SED fitting methods, which you can find at that paper. If we consider all of the basic ingredients that we think we need to evolve galaxies within our universe, they involve things like recipes for star formation, how gas cools, how stars and black holes eject feedback, as well as how do we just model gravity and hydrodynamics in our simulations. Around the outside here, I've got a number of different ways that you might want to describe these necessary ingredients. And as I step through each of the simulations that we have in the MAGPI survey, you can see that they all use a slightly different way to describe galaxy evolution. The variety and complexity of these recipes can make it quite difficult to understand which element in particular is going to help us reproduce our observations. And so for this, I'm saying we need to make sure we make our fair comparisons. So what do we have within MAGPI? How are we making these fair comparisons? This is where SimSpin comes in. This is a code that I wrote during my PhD to generate mock stellar kinematic observations of n-body models. It has since evolved in the last 2 years into a package that can be used for a variety of cosmological simulations to generate mock spectral cubes, gas maps, stellar maps, all for comparison with a variety of different IFU surveys. It's all open source and well documented on the website. It's aiming to be the sustainable code that can be taken and used and expanded on by a variety of different users for a variety of different science questions. I'll highlight that we just passed the 1,000 commit mark, and the paper to explain all of these updates is going to be on your archive soon. So how do we use it for MAGPI? With we then lay down our aperture and define some telescope specifics. So in this scenario, of course, we're using Muse. And we can then produce stellar kinematic maps, gas kinematic maps, as well as gas property maps. And we can also produce these spectral cubes that can be run and processed and tested through observational pipelines, such as PPXF in this example. We've got this for Eagle, Illustrious TNG, Horizon AGN, and Magneticum so far. We've got about between 1,000 and 8,000 galaxies in that necessary halo mass range that Trevor was discussing for each of these simulations for a rich data set for comparison with our observational data. And following a really successful ADAX development proposal, and with the help of Data Central and Liz Mannering and Simon O'Toole specifically, we've built a web application such that you can interact with this data in an exploratory way, building your own observations without having to download the code or a specific simulation. So you can use this to really start to explore the range of science goals you have. And in further collaboration with the DIA team and Sam Vaughan over at Macquarie, we're also looking to extend this so that you can allow batch production of observations to compare directly to different surveys as well, and the integration of directly with those simulations. And I think Richard will talk about this a little bit tomorrow. And that was some of the images. Okay, so lots of pretty pictures, but I'd like to tell you how we're going to be using some of these. So the first work I'd like to highlight is from the summer student who was working with me over the summer at ICRA, Alice Serene, who, again, in collaboration with another student from Macquarie, Ashik Burton, managed to extend SimSpin, that open source code, to work with TNG outputs. Once we'd done that, we started exploring the wealth of kinematic information we have in these mock observables. And rather than just measuring one value from our beautiful, exquisite 2D maps that we get from IFUs, we decided to start looking at how these processes evolve as a function of radius. So here we're looking at a spin ellipticity track where we measure within isofocal ellipses how those kinematics are changing as a function of radius. And in this work, we really wanted to compare back to the work of Rawlings et al. From 2019, which in this scenario was done for the SAMI survey. And in initial results, we were seeing a huge variety of differences between our simulations and observations, and getting to the bottom of that has opened a whole new thing to explore in the future. Hopefully, Alice will be joining us back to do a PhD. Another application for SimSpin and also just mock observations in general is it's an ideal way to test Schwarzschild modeling. So this is to highlight some of the work that Julia has been doing. She and I think quite a few Astro 3D members attended her excellent Dynamite workshop at the end of last year. This was one of my attempts to run Dynamite, a Schwarzschild modeling code, over a mock Eagle galaxy. So this was observed at our workshop. We had both MAGPI observations and SimSpin observations of these simulated galaxies. In the top, we've got what the actual kinematic maps look like. In the second row, we've got the modeled values, and the residuals are there at the bottom. As you can see, I didn't do very well on the dispersions, but I've been told that I could improve this with more work. And yeah, that dynamite workshop was a cool demonstration of how we could use our mock observations and real observations side by side. And finally, of course, with large and representative data sets such as these, they are ripe for machine learning opportunities. So we've been using some SimSwim mock observations to try and train models and get back to the intrinsic 3D shape of a galaxy, which is something that we know. If you're interested at all in this, talk to myself or Suki, who is also in the audience today. So hopefully I have convinced you that this comparison between observations and simulations is imperative to get to the bottom of galaxy evolution. If anything I've talked about today, please do come and chat to me. I'm always keen to talk about science. Thank you.